So good morning, everyone. Am I audible? Okay. Okay. So how about now? Am I audible? Okay. Thank you. So today is the last lecture of the GIAN course. I hope you all have enjoyed all the lectures and the tutorials that have happened so far. What I am going to do probably today is to upload all the lectures on YouTube and will try to share all the lectures with you privately. Uh, and regarding the current lecture of today, we are going to talk about seismic interferometry. So I am not going to actually show you slides for this particular topic because my main intention is to write everything out onto the OneNote, and then within the process of writing, you will get to understand this complex topic in a little bit of more detail. I hope that will work out and will give you a quite sufficient knowledge about seismic interferometry. So this is let's get started with it. Uh, so the topic is seismic interferometry. Okay. So the term uh, seismic interferometry basically refers to the principle of generating new seismic responses of virtual sources by cross-correlating seismic observations at different receivers. So let's suppose this is the this let's suppose this is the surface of the earth, and on top of which you have installed two receivers. And let's suppose this is your receiver 1 and this is your receiver 2. And these all both of these instruments are recording data, all kind of noise data from all the directions. Likewise, here also it is recording all kind of data from all directions, both the receivers. So the seismic interferometry says that the observations that you are recording at both of the receivers, if you cross correlate both of the observations together by keeping the source at one of the receiver, then what you will get after cross correlation is the response of the structure in between the receivers, or you may say the Green's function in between the receivers. So when I say Green's function, what does it mean? Green's function. So Green's function is basically the impulse response of the medium. So if I will define it, Green's function is defined as the impulse response of the medium. Okay, and if you will talk about with regard to a signal being received, then you can say that the Green's function translates to the Earth response between the receivers. So with regard to the signal, being received by sensors at two locations the Green's function translate to the Earth response. Okay. Now, the term seismic interferometry that we are talking about, the definition goes like this. The term seismic interferometry basically refers to the principle of generating new seismic responses of virtual sources by cross-correlating seismic observations at different receivers. So, seismic interferometry, what is seismic interferometry? So, the term seismic interferometry refers to the principle of generating new seismic responses of virtual sources by cross-correlating seismic observations at different receiver locations. At different receiver locations. Okay. So seismic interferometry so says that if you would like to find out the response of the Earth structure from the observations that you are recording at two receivers, you just need to cross-correlate the observations of the two receivers in order to get the response of the Earth structure. So by doing so, what you are doing when you're cross-correlating the responses or the observations at two receivers, you are considering virtual source at one receiver location, and considering that source, whatever energy that you are recording at the other source, that's basically termed as the Green's function or the response of the Earth structure. So seismic interferometry basically is of two types. So like one is controlled source seismic interferometry. Control source interferometry, you may say interferometry. And second is the passive seismic interferometry. Okay, so when I say control source interferometry, it is basically a new processing methodology for seismic exploration data, and it was basically uh, pioneered by scientists like Schuster. They published a paper in 2001, and McCullen, they and McCullen and Calvert. That is a paper that released after Schuster in 2004, and there were other scientists. So it is a kind of new processing methodology for seismic exploration data. New processing methodology for seismic exploration data. And apart from cross correlation, controlled source interferometry also involves summation of correlations over different source positions. So we may write this point also. Apart from cross correlation, controlled source interferometry also involves summation of correlations over different source positions. And if we talk about passive source interferometry, then passive source interferometry is used for passive seismic measurements like ambient seismic noise or micro earthquake response into deterministic responses. So passive seismic interferometry, it is used for turning passive seismic measurements like ambient noise or micro earthquake response into deterministic responses. Okay, so overall, in all cases, if we say in all cases, basically, uh, a response that is retrieved by cross-correlating two receiver recordings uh, can be, you can interpret it as the response that would be measured at one of the receiver location as if there were a source at the other. So this is what seismic interferometry does. So a response that is retrieved by cross-correlating two receiver recordings or in bracket you may write and summation over different sources summation over different sources can be interpreted as the response that would be measured at one of the receiver locations. As if there were a source at the well. So, this statement says that the response that you would like to generate, it will be generated by the cross correlation of the recording of the two receivers, where you are considering the virtual source is located at one of the receiver. Okay, so this is a two receiver case where you are considering like one source at one receiver and another as a receiver itself. And but you can do summation over different sources, because when you are keeping an instrument in the field, then all kind of source will be all kind of observations from different sources will be recorded over to the instrument. So you'll have to do summation over different sources. So uh, so when you are considering a virtual source at one of the receiver and having the response on the another, then that virtual source, or it may be known as the point source. So that point source response will be equal to the Green's function that is convolved with the wavelet. So that is why you can say that the seismic interferometry, often called as Green's function retrieval. So this is an important point. So because such a point, source response is equal to a Green's function convolved with a wavelet. So this wavelet is the source wavelet. The Green's function convolved with a wavelet, and in that case, seismic interferometry often called as Green's function retrieval. Green's function retrieval. So there are basically two assumptions associated with seismic interferometry. So we should know about those. So two assumptions. So the first assumption is the medium is lossless. That means the energy is not being attenuated. The medium is lossless. And second assumption that is there is the medium has constant propagation velocity. Okay. So after considering these two assumptions, let's talk about 1D analysis of direct wave interferometry. 1D analysis of direct wave interferometry. Okay. So let's suppose let's suppose you have two receivers, okay, and those receivers are located at position, let's suppose, let me put different. Those receivers are located at point XA and XE, okay, and there is some source over here which is basically uh, radiating and radiating, which is basically an impulsive unit source, or it is generating the plane waves. So let's say this is actually generating. Uh, so so this is generating plane waves like this. Okay. So we may write it down here that this is plane waves radiated by an impulsive unit source, which means it is generating the plane waves of unit amplitude, unit source at x is equal to xs and t is equal to 0, which is basically propagating rightward. Okay, and these are basically two. These two are the receivers at position XA and XB, and you can we can say like uh, so that these are the so at t is equal to 0, the plane waves are being generated by this unit impulsive source, and the response that will be recorded if I consider the origin to be located at the source position. Uh, the response that will be recorded at XA will be something like this. Okay, so XA will be something like this. So this is your XA position, and this is your the source position is the origin, and here you are recording your. So here you have recorded your response from the plane waves that are generated by the unit impulsive source. So this is the response that will be observed by this first receiver at XA will be, let's suppose, PA, and so this is your time axis. Okay, I forgot to tell you this is the time axis. So this is your basically response observed by the first receiver at XA and denoted as it can be denoted as G X A comma X S comma T. So where G basically stands for Green's function. G stands for Green's function. Okay, so where you can see in the entire class this G, XA, XS, comma T kind of things we will be writing more frequently. So so this at the first place, whatever we will be writing will basically represent the receiver, and at the second place, whatever we'll be writing, it will be representing the source. So, so this is the response TA that you receive at XA receiver. Likewise, the response that you will receive at XB receiver would be maybe somewhere like this. So here you have source position at origin, back again, and here you had your this is your XB position, and where you are recording your response from the source. Okay, so it is your TB. Okay, so again this is your time. So this is the response observed by second receiver at XB and denoted by G. Now it will be written as what? G, where here we will be writing receiver, then source, access, comma T. Right. So all in all, uh, the travel path from, you know that the travel path from access to XA is common for both the responses that are received at XA and XB. And when you will cross correlate the responses, this common path response will be cancelled. Okay, in case of cross correlation. So in D, what you can figure out is that, so like here you have when you will cross correlate, what you will found that here the we are considering we will be seeing the virtual source, and because the common path has been cancelled, and here at B you will be having the response due to the virtual source that is located at position XA, and that will be your TB minus TA. So again, this is your time. This is your time axis. Okay. So now let's write this out. The travel path from access to XA is basically common and will cancel in the cross correlation process, and will cancel in the cross correlation process, leaving the travel time along this common path from XA to XB. That means TB minus TA, that will be equal to XB minus XA divided by C. C is the propagation velocity. So hence what you can say, the cross correlation of the responses that you are getting in this figure B and figure C is an impulse at TB minus TA, that is shown in figure D. So let's hence the cross correlation of the responses in figure B and C is an impulse at TB minus TA. That is shown in C. So in D. Okay. Now, so this impulse that you are receiving can be interpreted as the response of source that is at XA observed by receiver at XB. That means the Green's function you can write maybe like this, because as I said to you that the first letter will be your receiver, second one is source, and third one will be the time. So we may write down, this is important, this impulse can be interpreted as the response of a source at XA observed by a receiver at XB. That means the Green's function that means G, that this is the receiver position XB, XA is the virtual source, and T is the time. Okay, so this is the Green's response that you are getting after cross correlating the observations that you are receiving at position XA and XB. So one important thing that you may like to note is that the propagation velocity C and the position of the actual source axis you don't have to know. It need not to be known in order to calculate the Green's function. So you will see like we are just cross correlating the noise that is or the seismic observation that is recorded at XA and XB uh, by considering virtual source at the position of another receiver. We are not taking into account the actual location of the source in this particular calculation, not even we are required with the propagation velocity. So an interesting, so we can write an interesting observation is that the propagation velocity C and position of the actual source axis need not to be known. Okay, so uh, we can write the equation of 1D Green's function as follows. So the following 1D Green's function represents uh, Green's function representation is obtained. So that is G. That is the final response that you get after cross correlating. So XB, comma XA. So B is the location of virtual source, comma XA, comma T is equal to G XB, comma XS, comma T, that is convolved with G XA G XA, comma XS, comma minus T. So, so this convolution, this is a convolution operator. So basically what I am doing, I am although I am cross correlating here, but the cross in convolution, what you do, you just reverse the time series. If you are convolving two signals together, then you will have to reverse the one time series, right? So that is what I am doing here. So I am reversing it so that it will still be working as cross correlation. So basically, so in order to understand, you will write it down like this operator denotes convolution, but time reversal of the second Green's function turns the convolution into a correlation, into cross correlation. Green's function turns the convolution into a cross correlation. So this equation that we have written here is basically true for unit impulsive source, right? So, but source will always not be unit impulse. It will having some finite amplitude or wavelet, you could say. So for that purpose, we need to write another equation. So this equation, you may write this equation is basically true for unit impulse source. Right. So this is the most simplest case that we have considered. And we will build upon it to consider where the source is having some finite wavelet. So in case, if suppose your source is of your source is generating a wavelet, okay, some wavelet, ST, then what would be the response? So that we can write down. If the source is defined by some wavelength instead of unit impulse source, that is an ideal case. Okay, by some wavelet ST, the response at XA would be what? Let's suppose in that case the response would be U XA comma XS comma T, right? This is the position of receiver XA, the response at XA. This is the source position XS, which is a wavelet. So it will be what? The Green's function at XA comma XS comma T convolved with the source wavelet. This is the final output or the displacement that you will receive as a seismogram. Okay, in the form of seismogram. So if suppose you have a unit impulse source, then this will become 1, right? But if it is a wavelet, then you will have to convolve it with the Green's function in order to get this U value. U XA XS comma T, the response at XA. Likewise, you may write the same thing at XB, response at XB, response at XB, and that would be your U XB comma XS comma T, and that would be equal to G XB comma XS comma T, that will be converted with ST again, right? So, so now let's suppose you want, so our theory says that, right, theory of interferometry says that the response should, we are, if you want to get the Earth's response, we need to cross correlate the two signals that are received at the position XA and XB. Okay, so we are going to convert that. Okay, so as per the theory, okay, let's uh, cross correlate them. So, so the u xa comma xs xs comma t, that will be cross correlated. So this cross correlation means if you are traversing the time series, then it will be a convolution. So it is a convolution operator. And for cross correlation, I will reverse the time series. Sorry. Okay, actually, I am sorry. Actually, I am considering the source at position x uh, xa, right? So now, I would like to see the. So basically, I would like to. So I am considering the source position at xa, and we'll try to see what is the response at xb. So the source. So what is the response at xb? So xb comma uxb comma xs comma t, that will be converted with the reverse time series xa comma xs comma minus t, and that will be equal to so we can place these terms like g xb comma xs comma t uh, s t, and then this is one thing, and then cross that it will be converted with g xa comma xs comma t, that is minus t because we are reversing the time series into s minus t, right? Here you have minus t, s minus of t. Now what you can see, this thing st, and that is having a convolution with s minus t is basically your cross correlation. So we can write that we can do here in different color. We can write here let SST be the autocorrelation of of the wavelength. That means SST will be equal to ST convolved with S minus T, right? So, we can incorporate that into the previous equation that we just wrote down. So, basically these things, uh, this thing here ST and S minus T will be your SST. So U XB comma XS comma T cross correlated with U XA comma XS comma minus T, and that will be equal to G XB comma XS comma T cross correlated with BG XA comma XS comma minus T, and then SST, right? So therefore, you can rearrange the overall equation. So this thing that you are seeing here, what is that? We have already written out in case of unit impulsive source. So you remember, like this is this thing here, right? So it is the rest. It is the Green's function when the virtual source is located at xb and being recorded at xa at time t. So we can replace it with that particular thing. Now, finally, we can say therefore, this thing will be written as G xb comma xa comma t, that will be equal to, oh, sorry, that will be converted with SST, right? This is G xb xa comma t converted with SST, and we are now here writing the left hand side, that is u x d comma x s comma t correlated with u x a comma x s comma minus t. Is that okay? Is there any question so far? Is there any question? Okay. So now, in the form of text, we can write it like if the source function is a wavelet, instead of an impulse, then the cross correlation of the responses, then the cross correlation of the responses then this is the cross correlation of the responses. Okay, uh, at two receivers at two receivers gives the Green's function. Gives the Green's function between these receivers. Which is converted with autocorrelation of source function. Autocorrelation of source function. So, so it's a okay. So now let's take a 10 minutes break. We will meet after 10 minutes at 8:30. Now I am back. So we have seen the case where the source is a wavelet source, where the we have seen like if the source function is a wavelet instead of an impulse, then the cross correlation of the responses at two receivers gives the Green's function between these receivers converged with the autocorrelation of the source. So now let's move ahead and take some real data example. Okay. So let's take real data example. Okay. Let's suppose there is a band limited noise source NT, band limited noise source NT. Okay, and that is located at position XS, like previously, and some of the features are like central frequency of this source is around 30 hertz of the noise is 30 hertz. Uh, so which means so let's which means and also let's take about distance between the XA. We are again considering those same position XA and XA. Okay, and the source is located. The source NT is again is located at the same position as we have seen in the previous example. Okay, so the distance between XA and XB, we are assuming that is maybe around 1200 meters. Okay, and let's suppose the propagation velocity that we are assuming, propagation velocity that is around 2000 meter per second. So at position XA, let's suppose at position XA, the noise that has been recorded at position XA may be something like this. So maybe something like this. Okay, and this is the response at XA, and here you have time, and it is a 4 seconds of the signal. Okay, so this time and 4 seconds of the signal, and there is another so response at XA. Likewise, at response at XB, maybe something like this. Okay, and this is again time. This is again 4 seconds of the signal. Okay, so basically, you can say the response that you are observing at XA. It may be represented as X cube XA comma XS comma T, that is equal to G XA comma XS comma T, that is convolved with the source pulse and T, and response at XB will be like this: U XB comma XS comma T, that will be equal to G XB comma XS comma T, that is convolved with source pulse and T. And now what you are seeing, if we cross correlate these signals as per our theory, then the cross correlation, what you will observe will be so this is the zero position of the time lag, and this is your maybe -1. This is your 0.5 minus 0.5, and let's suppose this is your 0.5, and here you have. So after you cross correlating the signal, what you will observe there is a energy at this particular time. So this, which basically uh, provides the impulse response. That means that is maybe around 0.6 seconds. Okay, so what you will observe if you look at the responses at XA and XB both, then at XB you are recording these signals, and at XB, because it is little far, so it will be recorded little, there will be a little delay in recording these signals. So you can see, so when you will see onto your x-axis in the time domain at the time, then you will observe that the difference between the timing is around 0.6 seconds. So that is similar to what you are getting after cross-correlating the pulse. So from this particular example, you can basically get to know that the
Sir, sir, what is NT?
this is just a noise source. This is the representation of the noise source NT. This is a source notation.
Okay.
So we are considering source here, NT, in the form of NT. Okay. So basically, this is the impulse response that is being provided by cross correlation. You can say like the cross correlation provides impulse response. Impulse response at 0.6 seconds. Okay. Now we can write an important statement here from our observations. So here basically what you are getting is 0.6 seconds is the travel time, right, between the receivers. You can see like this is the difference that you are having on your observations if you look at it clearly, and the same thing you are getting after cross correlation. So if you even have just the recordings of your signals at two receivers, if you will cross correlate them, then it will basically give you the travel time between the receivers. So just cross correlating the noise data that is recorded at your receiver, you will get that travel time between the receiver, and that travel time can actually help you to estimate the propagation velocity between the receivers, right? Because you know the distance between the receivers. After cross correlating, you get the travel time of the waves between the receivers, and then you can divide distance by time, then you will get the velocity, right? So that velocity is the propagation velocity. So you are getting the physical parameter of the Earth by just cross correlating the two signals that are recorded at the receiver. So this particular information is very much useful. So it basically illustrates that the direct wave interferometry that we are studying now can be used for tomographic inversion. In inversion, our aim is to find out the velocity, right? So that basic information can be found out just by cross correlating the receivers, the signals that is being received by two receivers. So now let's write that out. The above example shows that we can estimate the propagation velocity by dividing the distance between receivers by the travel time estimated from the band limited Green's function. Estimated from the band limited Green's function. Okay, so further you can illustrate that. So it illustrates that direct wave interferometry can be used for tomographic inversion. Right. Now that we have considered in the previous examples, our source was located at the left hand side. What if your source is located at the right hand side? Okay, then what will happen? So let's consider that case. So if we consider the leftward propagation of the noise, okay, so like we have done previously, we are not changing the position of the origin, it will remain same. So here you have your XA position where the first receiver is located, this is your second receiver located, that's B, and now here you have your source that is at the left hand side, it's radiating the plane wave in the in the leftward direction. So this is your XS dash, and which is basically radiating the waves in this direction. Okay, and your position of origin is again at the same position as that of the previous source, and so now, so so now because of this source, the pulse, the time of the pulse, let this pulse is again the unit impulse source. Okay, unit impulse source. Okay, so now this is radiating the plane waves. The time at which these waves will be recorded at XB and XA with respect to this origin will be like this. So at XA, so this is your 0 origin. So at XA, uh, it will be recorded, let's suppose somewhere here, TA dash, and at XB, because XB is near to source, so it will be near to the origin as well. So here is 0 origin, and this is your, so this is your TP dash. Okay, and so this is your x direction, this is your t axis, and when you will convolve to cross correlate both of the responses together, then what you will get TB dash minus TA dash because it is a unit impulse. Okay, and here will be your, I'm sorry. So here, here you will get TB dash minus TA dash, and here will be your origin. Okay, so this basically what it suggests. This correlation you may interpret as the time reverse Green function. Okay, because it is on the left hand side of the origin, because of the leftward propagation of the radiated plane wave. So the cross correlation may be interpreted as the time reversed Green's function, that is G XB comma XA comma minus T. That is the time reverse, right? So if you compare it with the previous Green's function, it is just the time reverse because the source is located on the right hand side and the wave of propagation is in the left hand side. So you can combine these two equations for both of the sources together. So now we can write, so a combined equation So basically what we are doing, first we have considered a source in the left hand side, next we have considered the source in the right hand side. So we will see combined equation of combined responses that are received at both of the receiver location, and then cross correlate them, and then we will move on further to see what if the source are located everywhere around the receiver position, which is actually the real case. Uh, so first we are building upon it like step by step. Now first we have done the one source at the left, and then we are right, then both the sources together. Then we will consider sources all around it. Okay, so the combined equation for both the unit impulse uh, sources at xs and xs dash can be written as g xb comma xa comma t plus g xb comma xa comma minus t, that is equal to summation over I is equal to 1 to 2, because there are two sources, uh, g xb comma xs, that is I comma t, cross correlated with g xa comma xs, that is I comma minus t, where xsi for I is equal to 1 comma 2 stands for axis and axis dash respectively, for unit impulse source, right? Likewise, you can write the similar equation for the source wavelet st. Likewise, for source wavelet st, we can write g xb comma xa comma t uh, plus g xb comma xa comma minus t, and that will be converted with the autocorrelation of the source wavelet as st, and that will be equal to summation over I is equal to 1 to 2 u xp comma xs I comma t cross correlated with u x a comma xs x s I comma minus t, right? So this is for source wavelet for both the sources. When okay, so is there any question so far? Okay, so now let's move on to consider a consider uh, many point sources uh, that we are going to talk about in 2D analysis and 2D analysis of direct wave interferometry, or you can say 2D and 3D analysis. 2D and 3D analysis of direct wave interferometry. Okay. Let's suppose again we consider the two receivers that is located at position XA and XB. Okay. And there are some so instead of plane sources, we are now going to consider the point sources, and we will denote those point sources by small dots that would be distributed over like pineapple slice. So like these, so in the previous cases, what we consider source here, and then we consider source here at both the position. So source position we have assumed like in the left hand side and the right hand side, but it is not the case in reality. In reality, sources are located everywhere, all around the receiver. So let's consider the sources are located here like this. So here we may consider the location of XA and XB. So this is XA and this is your XB. And sources are located all around it. Okay, these are the small dots. These dots are representing the location of the source on a pineapple slice. Okay, I'm sorry, my drawing is not that good. So we are considering a lot of sources here. Okay, like this. So these are the lot of sources here around it. These are the point sources. Okay, so these are the point sources that are around of both of these receivers, and because of these point sources, the noise, whatever is to be generated, will be recorded at the receivers that are at XA and XB. And this is the horizontal line. This horizontal line corresponds to the 1D configuration, similar 1D configuration with receiver XA and XB. Okay, so we can write horizontal dash line corresponds to 1D configuration with receivers XA and XB. Okay, and this is now let so this is your phi s. This is basically representing the polar source coordinate, and when you will so the response that you will see at XA with respect to this phi s angle, then it would look something like this. So here you have basically the phi s angle, which may be varying from -90. Here you have 0. Here you have 90, and here you have 180, and maybe here you have 270 likewise. And here you have 0, and here you have 0.5, and here you have 1.0, and here you have 1.5. Okay, and if you will see the for the receiver at XA, we are first looking at the response at receiver XA. The distance is smaller here. As you go on to increase the angle phi s, then the distance will keep on increasing, and then it will become maximum at 180, uh, which means the time here it will be the maximum at 180 degree, and then again it will reduce and will become minimum at the phi s is equal to uh, maybe 360 degree. So the response that you can make here, so here you have, sorry, yes. So the response that it will be recorded by XA will look something like this. So at position 0, it will be maximum, and at 180, it will be minimum. So the response, let's make it. So it will be looking something like this. So we can just make so it will be maximum, and then it will start to reduce after with 0 and will become maximum at, it will be minimum here and it will be maximum here at 180, and then again it start to reduce. Okay, likewise you can make the response at XB. Okay, so here you have phi s again, and here you have 90 degree minus 90 degree, here you have 0, here you have 90 degree, here you have 180, and here you have 270, and there the same values 0, 0.5, or maybe 1 and 1.5. And if you look at from XB, the maximum time it will take from here and minimum it will take from here, right? So accordingly, we can plot it. So it will be maximum at 0, right? And it will be minimum at 180. And when you will plot, it may look completely reverse of what you have seen at XA. So it will be like, let me tell you different color. So it will be uh, like this. And then it will become minimum at 180 degree, and then start to reduce like this, right? It is reverse of what you are getting at XA. So now these are the responses that you are getting at XA and XB. So this is your receiver XB. Okay, response at receiver XB. Okay, you have response. There is also response. Okay, now so these are the response that you are receiving at XA and XB. Our interferometric theory says that we need to cross correlate to see the response of the structure in between both of the receivers by considering the virtual source at XA. So when you do that, what you will get will be something like this. So this is the thing that needs to be done on computer. I am just showing you with some hand diagrams. Okay, so computer means some simulation need to be done. So the result of the simulation is this, that whatever I'm plotting now. Okay, so it is again 5 years here. When you do cross correlation. So this what I am plotting it here is the cross correlation of the responses at XA and XB. And when you will cross correlate these two signals with each other, when you will cross correlate, then it will be time reverse and then cross correlate them. And then what you will get will be something like this. So here you have minus 1.0, here you have minus 0.5, here you have 0, and here you have 0.5. Okay, here you have 1.0, 0.5. Okay, and here you have 0 degree, here you have 90 degree, here you have 180 degree, and here you have 270 degree. Okay, and then you will cross coil it, and then you will get something like this. Uh, okay, and what you will see that uh, when when you will sum them up, what you will see that this will be cancelled out with this one, and this will be cancelled out with this one, and finally things will remain will be concentrated within this particular 5S values. So this is basically the zone where uh, you will see the contribution of the sources, main contribution of the sources will be coming from. So this is these are the zones uh, from where the contribution main contribution of the sources uh, coming from. And these zones uh, are also known as Fresnel zones. Okay, so when you will sum them up, the response finally you will get maybe something like this, and then like this. Okay, so because this will be contributing to this one, and this will be contributing to this one. Okay, so such a gather that you have just made is also known as the correlation gather.
Sir, one question.
Yeah.
So this correlation looks similar to the XB and not XA. The second graph, why is that? Like, it should be something in between, or it should be like one of them?
Yeah, actually, when you will do the cross correlation of these two responses at XA and XB, you can do it in MATLAB as well. Okay, so what graph you will produce will look something like this. This is the observations that we have seen. Okay, so that is what I am making, and then when you will sum them up together along all the azimuth, along all the polarization, along all the phi s values, then finally what you will get, you will see the main contributions are coming from the sources which are located at phi s is equal to 0 and phi s is equal to 180 degree. So all the sources along this direction and this direction will be cancelled out with each other. Only the contribution will come from these sources and with these sources. Is it fine? Hello, am I audible?
Yes, sir, that's fine. Yes, sir, thank you.
Okay, so now, so this is what I wanted to talk about in the seismic interferometry. That's the basic knowledge I wanted to disseminate to you. What now I would like you all to do is to read that paper which we wanted to read yesterday in the yesterday tutorial. And one more paper I am now sending it to you. So that is regarding the theory that we have discussed today. That is the paper from Wapinar, which was one of the earliest paper in the field of seismic interferometry. And so let me send it to you. So, okay, okay, read this paper first, the webinar paper, because we just discussed about the theory that is within this paper. Okay, just read that paper up to maybe uh, page number up to like there is no page number. Okay, 198, 199. So 75A 199. So please read this paper and see what you can make out of it. I hope today's lecture was quite clear to you. If you still have any question, please go ahead and I am here. Okay, please read the paper. if you have even any question from the yesterday's tutorial or yesterday's lecture, uh, I am here to answer all your questions. Uh, I hope you might have seen the tutorial things yesterday. And, associated video I have uploaded already on YouTube. I am in the process of uploading all the videos on YouTube and will send them to you very soon. So there is this another paper for which I have sent you the link in the chat box. This paper is also a very important paper which basically talks about the processing of ambient noise data uh, for reducing the surface dispersion measurements. So this was published in around I think 2007, and then it talks in a whole lot of detail about the steps that you need to follow in order to calculate range function from the real data, and then also subsequently talk about the frequency time analysis for the computation of the dispersion curves from uh, from the green function. The green function that we have just read about after cross-correlating the green function that we are getting, that can further be used to reduce the dispersion curve. Okay, so those dispersion curves can be modeled to actually relate it with the subsurface structure of the Earth and the shear level of the models. Uh, so for that purpose, you can do inversion, you can do over modeling, and there are several codes available for doing so. I am sending you the paper. Then. Yeah, now it should work. I sent you the link again, and in this should work. So this is the paper which published in Geophysical Journal International. So it has all the steps, and you can uh, easily go through it. I don't think it is so difficult to understand. Yeah. And here is the link to a code for seismic noise tomography. It is a collection of Python codes, and the paper associated was published in 2015 by Kuturbe for doing the correlation of the seismic noise recorded on the broadband stations in the area of Dardi. So here is the paper, and this code is pretty good. And I see some people working on this code, publishing results into major geophysical journals. And this is also a very another very important course in Python. So that is also included very good. MS and noise. There are some documentation also available on the website of MS and noise. So that documentation will be very much helpful in order to understand the field. And then there is the computer programs in seismology that I shown you yesterday that also has its own utility for the cross correlations of the noise data to compute the green function. So you can see in the surface sections. So they have done some cross correlation ground noise example for the southeastern space, cross correlation of the ground noise with data sets. So these are also very important. We would like to go through it. So I think that is all I have for today's lecture. So for the tutorial, we will be meeting in the evening at 7:30 p.m. So this was the last lecture. I hope you all have enjoyed all the lectures that has been delivered so far. And you are most welcome to give the feedback on the GIAN website about this course. So thank you very much. We will meet again in the evening.
Thank you, sir.
Thank you, sir.